I'll let the interns introduce themselves, but first I'll introduce our two sign language interpreters, Francine Arnold and Mark Riley. Okay, the interns will introduce themselves.
Hi, I'm Asma, Shiekh, and I'm a bioscience major.
My name is Darrel Gumbs. I'm majoring in laboratory science technology.
I'm Saki, and I'm a graduate in life sciences, and now I'm continuing my education with Fahmida.
Hi, my name is Erin Hoover. I just graduated from laboratory science technology. I'm majoring in technology now.
And our laboratory team leader is operating the camera. That's Darrel Gumbs. Okay, I'll let the interns take it away. Thank you so much.
So, fiber membranes. By way of introduction, what do we mean by a fiber membrane? It's a useful membrane is good for a barrier filtration, water, gas filtration, water, oil separation, cell membrane filtration, hemodialysis. There are many different uses for fiber membranes and filtration applications. So we want to know what makes a good filtration membrane. We're particularly interested in the separation of water and oil. We're looking at the mechanical properties. We want to, again, separate oil from water in our application. We're using a copolymer as part of our material that is important for this filtration application. Let me show you a picture so you get a visual, good idea of how these work. This is one example. We have water represented out by our solute particle, and solvent goes through. The green arrows here where our membrane is. We didn't work on this particular membrane on the right, but it shows you, various applications, parasites, water, bacteria, salts, biopolymers, and so on. So our goals here this summer, we want to make a filtration membrane out of fibers. And we're looking for specific diameters in our fibers. We're evaluating the performance of the membranes. And we're using the material called PVDF, which is blended with another polymer, Zwitter ionic. And with these materials, we're hoping to make high-quality membranes for filtration and separation. So it's important to talk about what is a polymer. Polymers are made of monomers, which align in chains. They can be very, very long chains. They are connected by covalent bonds. And we're particularly looking at PVDF, polyvinylidene fluoride, which does set up in these chains, as I mentioned. And here's a little bit more in-depth explanation about PVDF. Its melting temperatures around 150, 180 degrees Celsius. Glass transition, which is important for us, is around 30 degrees Celsius, minus 30 degrees Celsius. And within this material, we have about 40 to 60% crystalline structure. And again, melt temperature is about 150 to 180 degrees Celsius. So these characteristics are very positive. It's recyclable, which is also very good. And it mixes well with our copolymer, which is sp2VP, which I'll explain as we go forward. And you can see the chemical structure here. So we're making filters as our ultimate goal, and we're mixing PVDF with a copolymer, sp2VP. You see the chemical structure here. We're also using PMMA, another polymethyl methacrylate as a third part ingredient in this mix. So here's a visual representation of what our blend of these materials, PVDF with the copolymer, would look like. So we're clear. Any questions? Are we good? So let's talk about the materials we use. We use for our solvents acetone and DMAC, dimethyl acetamide. We also use PMMA in PVDF. We are also looking at the additives of CNT, carbo nanotubes, and ionic liquid ethyl ammonium nitrate. So this looks darker because this is a photo of one that has the CNT, carbon nanotubes within. And here's our starter material, PVDF pellets. The solution preparation, this is my notebook, which sort of gives the recipe. We're putting in our PVDF, and we're looking at a 90-10% blend. 90% PVDF and 10% our copolymer. We mix them separately. We add DMAC and the ingredients I mentioned. Carbon nanotubes go in at 1%. It's a very small percentage of the overall mix. We mix them in jars. This is a mixer, the stirrer that we used. Everyone, I want to talk about a technique we call doctor blading of thin films. You can see in the picture, this is the actual doctor blade, the instrument we use in this technique. So we have our solution that we prepared, put that onto glass slides or glass plates, and then we actually, what we call doctor blading. We bring the doctor blade across the solution on the plates, and they spread out. We are looking to set up a specific gap in beneath the blade where it will make contact with the solution on the plate. So we're looking for a specific gap there that allows the result to be what we want. So we doctor blade, draw the blade across that, let that puddle that's left dry. We peel it off with a razor blade, and we get a film. And you can see in the picture, this is the vacuum table underneath the 4 glass plates that you see. And on the glass plates, this black one, that includes the 1% carbon nanotubes, that mixture. And these are 4 different mixtures we use that we doctor bladed to get what you see in this photo. And these are films that result from our solutions on the plate after doctor blading. And now we'll talk about another technique, electrospinning.
Part of the process is on the left. As you can see, we have the startup right here. Let's just put in a technique that uses high voltage in order to coat the polymers molecules and make it go down with fibers. We use different diameter needles in order to change the fibers. We use 18 gauge, 20 gauge, 22 gauge, and 24 gauge. The fibers are charged and look for a grounded area to release the charge. Since the collector plate is grounded, the fibers are on the collector in random order and make fiber mats. As you can see here, we have the fiber mat on the collector, and this is the fiber mat without the collector. Electrosplitting is used to make many products. It's used in filter media, protective clothes, and composite reinforcement. For filter media, it's used for filter membrane, charge filtration, and reverse osmosis. For protective clothing, you get cover glass, and composite, you get fiberglass and reinforced polymers. And so this is the setup. Right here we have the syringe pump. We load the syringe into this pump, and it goes into this properly coated chamber. And all the polymers land on the collector plate. We connect the high voltage to the needle in order to pull the fibers out of the needle, and they go through this opening in the Teflon chamber. So how it works. The syringe pump is usually set to pump out the solution 20 liters per hour, or depending on how much fluid you want to do. The collector plate is covered with aluminum foil and positioned in front of the opening of the Teflon chamber. The glass syringe is filled with this desired amount of solution, and the needle gauge is capped and placed in the syringe pump. The collector is grounded in position 15 centimeters from the tip of the needle. The high voltage is connected to the tip of the needle in order to create a magnetic field. The chamber is then closed and the pump is turned on. The second chamber is used for protection against the high voltage. It's closed. Then we turn on the high voltage, which is normally 20 kilovolts. It's very important that once the high voltage is turned on, that we never open the second chamber, or you get electrocuted. This picture shows polymer fiber membrane on foil on the collector plate. The reason why it's so gray is because the fiber membrane has carbon nanotubes added inside. The two pictures show an example of a good spin and a bad spin. As you can see right here, we got a whole membrane on the fiber mat, on the aluminum foil. Right here, you don't see anything on the foil, it's just a very long roll. And we want a flat surface like the first one. Now, let's see scanning electron microscope. The SEM is an instrument that allows us to observe individual fibers. The observation of the fiber diameter allows us to compare different fibers. The samples in this instrument are cut out from the electrospin fiber mats. The samples are coded using the sputter coder. So how it works. The sample for this instrument is cut out from fiber mat and then coated. These samples are attached to a stub using carbon tape. We coat these fibers with gold plating alloy using the sputter coating. After sputter coating, we place the sample inside the SEM holder. The holder is then placed inside the instrument and fiber images are taken on this computer screen. These pictures are two examples of what we see in the SEM. This is a bad picture because we see really big fibers, hooks in fibers. The diameter of fibers are not uniform. Here, however, all the fibers are uniform. You can see individual fibers. And here is a comparison between two different solutions I would like to say. 15% PVDF with 22 gauge, 50% PVDF SP2PP, 22 gauge. At 10x, you can see that the fibers look really far you probably can't be able to see the visual one. Then we go to 2500. As you can see, the fiber look a little closer. You can probably distinguish the individual fiber just by looking. You probably have to look really hard though. And then 5000X is when you can actually see every fiber individually, which is good for comparison to see if the fibers are close together, separated, or if you have any clumps that are very small but you can't see it from all the other applications. The 22 gauge is referring to the diameter of the needle. The larger the gauge, the smaller the diameter of the fibers. And then we get to the results. After we take those images, we place them in our software called ImageJ. The data in ImageJ is applied, and that will make histograms. The histograms let us know the average size of the fiber. As you can see here, this is a solution of 50% 9-10 PNT code. 22 gauge has an average fiber of 0.3857 micrometers. The old refers to the old CNT was very big. We have a new one mid-process, but they're smaller. And right here is comparing the old and the new CNT solution. The same thing, the different gauge, and shows that the new one, which is smaller, has 0.41 micrometers. The old one has 0.286 micrometers. Here is a comparison to PVDF, 50%, 20%, and PVDF with 0 co-pilot at 5,000X. The pictures from the last slide correlate to these graphs. As you can see here, a 50% CNT has average of 310 nanometers. 20% PVDF has an average diameter about 365 millimeters. And 50% with ionic polymer has an average of 360 nanometers.
Another technique we use is called the contact angle. So in this technique, we use what's called the sessile drop method. We have a syringe, and below that in this photo you see our fiber membrane, our sample membrane that I just pointed to. We drop. First of all, we want to make sure our surface is very clean and very flat. So we have the syringe above, and there's a droplet of water hanging from the syringe. We lift the platform with the membrane on it, and it makes contact and grabs that drop of water, separates it from the syringe and onto the membrane as we lower the platform. As you can see here. We have some pictures of 3 different samples. First one, second, third, and further illustrations. So in this sample, we have some wrinkles. It's not quite flat in our membrane. Over here, we have some areas that give us good flatness for this. The procedure, we're looking to find a flat surface on the sample for the water droplet. If we don't have a flat surface, we don't get a good measurement of the contact angle. And in this picture on the bottom right, we do have a good flat surface, and we found that we had a high contact angle with that sample. This is an illustration of the contact angle. You see on this line, we have our angle. So when the droplet, the circular part of the illustration, is on the membrane below, when we have above 100 degrees in terms of the angle, that is a good result for our purposes. If the surface wasn't flat, that droplet wouldn't quite be in a position where we could measure it accurately. So we want to have that flat surface with the water droplet sitting on it to get a good measurement of the contact angle. And in these graphs, you see some of our results. PVDF over on the left, unfilled with CNT fibers. And in the middle, we have PVDF with SB2VP, unfilled carbon nanotube fibers, and the third one is another of the results, unfilled CNT. Most of our results found that we had a high contact angle, meaning that the membranes are what we call hydrophobic. See, these two here, the degree of hydrophobicity is a little less, but pretty much all of them had good results in terms of the hydrophobicity, meaning they sort of want to keep water away. They don't like water. And now we'll turn to Erin for the FTIR.
Hi, so I did the FTIR, which is water transform and spectroscopy. What does FTIR do? It's used to collect the absorption at a different frequency, which is called a wave number, that creates a set of peaks from structure around materials. There are 4 different kinds of peak resolution, which is well-resolved, partially resolved, unresolved, and unresolved solar. We set the resolution at 4 centimeter peak closer together, then will not be resolved. So this is an example of 4 other peaks that I mentioned about the well-resolved, unresolved solar, and partially resolved. FTR also helps us to identify the alpha, beta, and gamma of the crystal of PVDF polymers. Therefore, we use FTIR to examine PVDF, SB2BP, ionic liquid, and carbon nanotubes on both fibers and belts to find the peak from different types of PVDF crystals. So these are the materials that we use in FTIR, which is samples of PVDF, SB2BP, ionic liquid, and carbon nanotubes. Tweezers, methanol cleaning, and microscope lens cleaning paper to clean the crystal. This is the picture of the FTIR that we use. So there are 3 different kinds of beads, which is beta, which is on the top, alpha, and gamma, which is this arrangement of the bond is help us determine which crystal phase we have in our materials. As I mentioned about 3 different phases, this is an example of how it looks with the peaks. So for the alpha, you see how the phase out. This one helps us tell that this is the alpha. As for the gamma, this one little key right here helps us identify gamma. As for beta, they look almost identical with gamma, but you just see how it has a little difference. See the line, it looks like that. Gamma. other way to help us to beta, which one alpha, beta, and gamma, is the centimeter. So, in our spectrum, we found the PDA to be close to 1275, which is beta. And then we found a 1234, which is gamma, and a different material that we used to study. Since I did some samples, and collected all the samples, I did 50% PVD of films. And it shows us it has majority of gamma. There's a little bit of beta. So, as I mentioned before, how to help us identify the gamma, you can see how it has to peak. It helps us to send that to gamma and not beta of how it peaks. I also did the comparison with film and fiber. So I used 50% PVD of film and 20% PVD of fiber. As you can tell, they look almost identical, but you can see the difference of the peak, like where there's a line arc. And it's because it's majority gamma beta with a little bit of gamma beta. So I also did only just the fibers to see how the peak looks like with just the fibers. And it just shows that it has a majority of beta with a little bit of gamma. On this line, it just tells us where it is. But it stopped at around 1272. But it's when I showed on the table. It's not exactly the same number on it, but it's closer to it. So it helps us to say that this is what it is. I also did the same thing with film, just the film only. And it shows that it is around 1232. It's not exactly at the same number again, but it's closer to what we have on the table. I also, not only did I do just FTI, I also do X-ray. The X-ray materials is examples that we use is PVD, SB2BP, ionic liquid, and carbon nanotube. We also use silicone wafer, which is the sample holder. Like with the silicone wafer, you put the sample on the top, and you put it on the sample compartment. This is the picture that we use for the X-ray. What does X-ray do? It's an electromagnetic radiation that has high energy and short wavelength. X-ray also interacts with the electron of the sample. It is similar to reflection of the surface. The reflected X-ray goes at an angle called 2 theta toward the detector. The x-axis is of the blood will be 2 theta angle. The detector tells how many X-ray comes every second. The y-axis of the blood will be intensity. It's the number of counts per second. So I also did 20% films. And you can see how the film has almost has a majority of gamma on there as well with the P in there. I also did a comparison between film and fiber. They also help us in how the P's are with the gamma and beta. The red line is the film which has majority of gamma, as I mentioned before, and the blue line is the SB2BP fiber. I also did just the fibers only. It was confirmed that each sample has a peak of beta physical phase. But there is a strong peak at about 21 degrees and a weak peak at about 37 degrees. The electrospon fibers is crystallized in beta phase. There's a possible reason why because the molecule of PVD was stretched during the spinning of electric cords. And And this line right here is the cell calculator. It to help us to subtract from the background. And this line right here to help us with the data with the degrees I mentioned of 37 degrees. I also look at the films. In this small piece of clickable base, and PD confirm that that path majority of paper. The strong peak will show at about 21 degrees, and the weak peak will show at about 27 degrees. The downward peak is the sun coverage as I mentioned. That is subtracted into another example. So in conclusion, we have that all our fibers have a beta base because of the stretch of during electric spinning, and our will have a gamma base.
I ran the test using the thermogravimetric analyzer, TGA. You can see in the photo that's the TGA itself. We use this to determine mass that is remaining in our samples as we heat them. And we look at when the mass starts to be lost at 50%. It's another point we want to look at. We're also looking at the major degradation of the materials under heating. So we're looking at this because we want to determine heat stability of our materials. So there's a little basket that we put our sample in, very small, you can see it right there. Our sample goes into that basket. And here you see Erin, she's actually cleaning the basket. You can see again how tiny that basket is. There's a little handle on the top of the basket. We put it into the instrument, which has a wire that lifts the basket up and puts it into our furnace. These results are for PVDF at 15%. And you see the red line, you can see where it starts to drop off. And that's when the mass starts to be lost from our material. And we go down below, and that's where it comes flat again, and that is where our mass is basically stabilizing. And here, the black line that goes across, that's our point where 50% of the mass is remaining, and that's happening at about 470 degrees Celsius. So that's where 50% of the mass is gone. And we're using also, on this line, the derivative. That's where we can determine the major degradation, which happens at that peak you see in the middle of the purple line. Also to add here, you might wonder why our material doesn't go to zero. There is a little bit of material left in the basket, what we call char, which remains. It doesn't completely burn off. So the line stays at that level. So here we have a comparison of PVDF, a 90-10 mixture, and the SP2BP. And you can see the purple line, the SP2BP, starts to lose its mass very quickly, early in the heating. The 90-10% means it's very close, a little less than PVDF alone. You see these lines, they are very close to each other. So it's a good illustration of our results on this graph. We also tested ionic liquid. That was one of our materials we were looking to mix in, and we determined that that was not a good ingredient to mix in, because you see that it loses its mass very, very rapidly, very early in the heating process. The 90-10% plus the IL, you can see right about here. The purple, we have the PVDF losing its mass starting here. The ionic liquid is lost here, and then further on we see the PVDF. Let me back up a little bit here to show you on this line. You can see the different lines, all those 3 lines in the previous graph are mixed into one here. You see the different points where mass is being lost and the different materials in the mix. And looking at this, we realized that the ionic liquid was not good because it doesn't maintain its stability under heat. Whereas carbon nanotubes are very strong and stable under the heating process. So, looking at CNT alone, 9010, 9010 plus CNT, you can see on that line at the top that goes far across the graph, it remains stable under that higher temperature heating. And 9010 with CNT, we see that here. Again, it's very close to our pure 9010 mixture. So that's, again, good result. Shows us that CNT is strong, very stable under heating. So analyzing our data, we made some comparison, SP2VP, 9010, PVDF, both of those. So at 450 degrees, the 9010 mixture is completely melted, gone away. And that's at the same temperature point where the PVDF mass loss starts. So SP2VP, the mass loss starts around 200 degrees and then drops off pretty quickly after that. We also show you here in our graphs. There's the 9010 SP2VP, pardon me. And again, the PVDF starts to lose its mass later than SP2VP. I also worked on an instrument and a technique, which is the differential scanning calorimeter. So this is an illustration of it. We're testing, again, temperature, materials under temperature. We heat using a sample and a reference within this instrument. And we're doing 10 degrees Celsius heating per minute, comparing our material to see where it melts. We also cool it. We look for a reheat to see where crystals, in the cooling where the crystals show up, and the reheating where it melts again. And you can see it's very small here. We have it toward the top of the screen right here where my fingers are. One is for the reference and one is for our sample. And there are 3 lids sitting here. And we stack those to run the test. So our sample, we have a pan, very, very small. We put our sample into the pan, make sure it's, the right fit within the pan, and we put our lid on top. We use a punch to crimp it down before we put it into the DSC itself right there. In this graph, we're seeing some of our results. PVDF fiber in this graph. We have the first heat 1, then we cool at heat 2, our second heating, you can see here. And we're looking at these regions where that peak is, the area under peak and the downward peak here. You can see they're close in the temperature range on our graph. Here's another result, PVDF with carbon nanotubes. If you see here the area of the peak, it increases with the CNT. You can see that it's a little subtle in the 2 graphs, but it is there. So this is looking at heat 1 only, with all of the samples. The various lines are representing the different materials and mixtures we use. And in this table, you see this, we're looking at the area for each sample, and we documented those in our table: heating, cooling, and heating again, first, second, and third on the table. So we're looking at the area of peak and we calculate crystallinity. We're looking for crystallinity. We do our calculation. We divide by 104.6 joules per gram to get our crystallinity. PVDF right here. And you can see the calculations here. We came up with 0.44 as our measure of crystallinity within the sample, which means, I should say, at the peak areas, we're also dividing by 0.90. So we have 0.90 because it's 90% PVDF. And this is, again, the final result, we determined that we have 44 material that's 44% crystal, 56% non-crystal. And again, the calculation, we have all of the different numbers representing crystallinity based on first heat, cooling, second heat. It's very interesting, these numbers, 44, very close in those three different temperature points, 52 in the first heat, and the second heat for 9010 CNT, also interesting. Before we go on to our conclusions, we also, as we did our analysis, we noticed that when we add CNT, we get more crystals, a higher degree of crystallinity, which is another important result of our research. So I want to talk about our conclusions. See the addition of carbon nanotubes results in a smaller diameter fiber when it's blended with PVDF. The PVDF copolymer with CNT gives us a smaller diameter fiber. So the X-ray shows that the fibers do have crystals in beta phase, probably due to the molecule stretching during electrospinning. The results of infrared spectroscopy confirm the results of our X-ray diffraction. We didn't see any alpha phase in PVDF. Fibers produce more beta phase PVDF crystals. Films produce more gamma phase PVDF crystals. The results of the DSC indicate that all as-spun fibers were crystalline and showed an endotherm. Upon cooling, the PVDF recrystallized, and during the second heat, the reheating, the crystals did melt. The crystallinity is proportional to the endotherm area, and our results confirm that the addition of CNT increased the fiber crystallinity. The contact angle measurements indicate the fiber form and the addition of CNTs both increased the hydrophobicity, whereas film form and the addition of sp2bp copolymer actually decreases the hydrophobicity. Looking at recommendations for future work, we collected our data with the various instruments. We learned very much about PVDF, sp2bp, the ionic liquid, and the carbon nanotubes and their characteristics, the environmental habits, behavior of dissolving with other solutions. So our next goal would be to form a fiber membrane with PVDF having a diameter of 200 nanometers or thinner, as much as possible, to be good for filtration. We want to test more polymers to see if PVDF would blend with them as well. And this is our poster and the picture, which is in the back of the room today. We would like to thank our sponsor, the National Science Foundation, Dr. Laura Place, our interpreters, Mark and Francine, Jonathan, Nelica, and of course, Professor Cebe.